Let's get started by first looking at the concepts underlying multi-vector retrieval. To help you get oriented, let's start by seeing how it works for text. Let's dive in. I assume if you are taking this course, you are already somewhat familiar with the fundamentals of vector retrieval and concepts like dense embedding vectors, vector similarity, approximate nearest neighbors algorithms, and the HNSW indexes that power them. If not, I highly recommend you take Quadrant's first course here with deep learning, which introduces you to all those concepts. Either way, let's do a quick review of what retrieval is and how it works. Retrieval is important because LLMs can't possibly be trained on all information relevant to the prompts they will receive. Retrieval augmented generation, or RAG, pairs an LLM with a database of relevant information. When the system receives a prompt, it will quickly search the database and retrieve the most relevant documents. The original prompt is then modified to include the retrieved documents, allowing the LLM to consider that information while generating its response. RAG can significantly improve the quality of LLM responses and is one of the most widely implemented types of generative AI systems. For example, a customer service chatbot will be much more helpful if it can access your company's product and policy information. Companies achieve that by pairing an LLM with data sources from which relevant information can be retrieved. The most common type of vector retrieval is called a byencoder. Every document in the knowledge base is assigned a vector representation by an embedding model. When a query is received, it is also embedded to a vector. The system will then search the database to find the documents whose vectors are located closest to the query vector. The primary benefit of byencoders is that they are very fast. One reason for this is that the document vectors can be pre-computed ahead of time. Even if you have 1 billion documents in your database, you only need to generate their vectors once. At search time, you are only generated a single vector for the query. The search process itself is also extremely fast. Thanks to the use of approximate nearest neighbors algorithms, they easily scale to billions of documents. The main issue with the byencoder is that they essentially compress the meaning of each document and prompt down to a single vector. This kind of averages out the meaning of the documents and prompts and can miss nuanced connections between them. Cross-encoders take a different approach. The full text of the query and document are fed to the cross-encoder neural network at the same time. This lets the cross-encoder detect nuanced relationships or interactions in meaning between the query and document. The cross-encoder will then directly output a relevance score, which can be used to rank documents. Cross-encoders tend to produce very high-quality results, but they scale horribly. Since they require the full document and query text to generate scores, no precomputation is possible, and every document you score requires a computationally expensive forward pass through the neural network. As a result, cross-encoders are only feasible to use when searching small numbers of documents, usually 100 or fewer. The best use of a cross-encoder is to re-rank the results retrieved by other techniques. Let's say you had 1 million documents to search through. You can use a byencoder to quickly find the 50 best matching documents and then re-rank those results with a cross-encoder to find the 5 absolute best matches. Ideally, you'd have a technique that enables precomputation, like a byencoder, and deep token-level interactions between the query and documents, like with a cross-encoder. Multi-vector techniques were introduced to do just that, so let's have a look at how they work. The most common multi-vector technique for text is called Colbert. Let's see how it works with a simple example. Let's say this is the text of your document. First of all, the text is split into tokens. Next, these tokens are each assigned their own embedding vector. These vectors not only reflect the meaning of that particular token, but also its meaning in the context of the whole document. If this were a byencoder, the next step would be to reduce all these vectors down to a single vector through a process called pooling. The most common pooling approach is to just average all these vectors, giving a single vector representation of the whole document. In Colbert, however, you keep all of these vectors. The process of representing a query works identically. The query text is converted to tokens, and each token is assigned a dense semantic vector. Now, let's score this query document pair. The approach is called maximum similarity or simply max-sim. The idea is that each query token finds the most similar document token. This is what it looked like for a token puppy. The vector for puppy is compared to the vectors of each document token using a typical vector distance measure like the dot product or cosine distance. Here you would expect it to match most closely with the token dog. This process is then repeated for every token in the query. The maximum score of this query document pair is then just the sum of the maximum similarities over all the query tokens. Maxim is different from other distance measures in that it is asymmetrical. The distance between A and B is not the same as the distance between B and A. To convince yourself of that, imagine you just flipped the text used for the document and the query in the last example as shown here. Originally, the maxim was the sum of 3 dot products, but now it's the sum of 5. As a result, you can take advantage of the highly optimized approximate nearest neighbors algorithms that typically power vector search. The issue arises when you try to build the HNSW index that the algorithm uses for search. This graph relies on knowing the distances between each document and a few of its nearest neighbors. Since maxim is asymmetric, A might be a nearest neighbor of B, but B isn't necessarily a nearest neighbor of A. This inconsistency prevents building the graph at all, and so when you're using multi-vector search, the HNSW index is usually disabled. Colbert ultimately delivers on its goals. It allows precomputation of vectors like a bioencoder, while the late interactions between the query and document tokens emulate cross-encoders. Since HNSW cannot be used effectively for multi-vector retrieval, you rarely use them alone for search over bigger datasets. If you did, then you would need to perform a brute force full-scan search over all the documents, which is too slow to use at scale. A more common way of using late interaction models is as a re-ranker of the results of faster techniques like a bioencoder. Typically, a faster retriever is used with oversampling, meaning you retrieve more documents than you eventually want to return. You then use the multivectors as a re-ranking step, so the maxim is only calculated on a limited set of candidates. The biggest downside of Colbert is the amount of memory it requires. With one vector stored per token, you can easily have hundreds or thousands of vectors stored for every document. These numbers add up quickly, especially if you have a million scale setup, which isn't that uncommon nowadays. Imagine your document has 1,000 tokens. Each of them gets a 128-dimensional embedding, and each number is represented by a 4-byte float. That's half a megabyte just for the vectors. A bioencoder only stores a single vector per document. Even if your vectors are very high dimensional, you usually won't exceed even 10 kilobytes per document, which makes the scale easier to manage. Late interaction models are a middle ground between single vector embedding models and cross-encoders. They need more memory and are more expensive to run than any other embedding models, yet they still allow to pre-compute the representations of the documents and do not require to pass them through the neural network for each query. More recently, we started to see much value in applying similar methods to other modalities than text, and they also seem to be working better than their predecessors. Before we discuss different modalities, let's explore how late interaction models are used in practice. We'll start by loading Colbert v2, a late interaction model developed at Stanford. Colbert encodes texts into 128-dimensional vectors for each token, enabling fine-grained semantic matching. Let's load the model into memory and see its embedding dimensionality. It's 128. Before we create embeddings, let's understand how Colbert processes text. Tokenization is a process of breaking text into smaller pieces that the model can process. Colbert uses word piece tokenization and adds special tokens like CLS at the start, unused one for document encoding, and SEP at the end. Regular words are either represented as separate tokens, or sometimes a word might be split into multiple tokens too. Let's define our document. We have a simple helper method to handle the tokenization process. If you are interested in the technical details, feel free to check the function definition in the helper.py file. Let's see how our sample document gets tokenized. Majority of words are represented as single tokens. However, decibels is split into 3 separate tokens which are on a subword level. Let's simply check how many tokens our document was divided into. Our document consists of 55 tokens. Now that you understand tokenization, let's create embeddings for your document. Unlike traditional dense models that produce a single vector, Colbert generates one embedding vector for each token, and as you saw, our document has 55 tokens, so Colbert should also create 55 separate 128-dimensional vectors, one for each token in the tokenized sequence. Notice the shape. This confirms we have 55 token embeddings, each represented by a 128-dimensional vector. In practice, when working with longer documents or data chunks, you can expect hundreds of tokens per embedding, but the principle remains the same: one vector per token. Now let's define and encode your query, which is way shorter than the document. Colbert encodes queries differently than documents. It pads queries to a fixed length or 32 tokens to ensure consistent comparison across different queries, but it also assumes a query cannot be any longer. While your query has only a few words, Colbert will generate 32 token embeddings with extra padding tokens to reach this length. If you make it longer, it may get cut off. As expected, we got 32 128-dimensional embeddings, even though our query was relatively short. Let's see how the tokenization of the query looks like using the same helper method like we used for the document. It has an additional parameter to control whether we create tokenization for the document or a query. As you can see, majority of the tokens are just some padding tokens, which are automatically added to the query. Nevertheless, each of the words of the original query was just converted into a single token. Now let's see late interaction in action. We'll compute the similarity matrix by taking a dot product between every query token embedding and every document token embedding. This creates a 32 by 55 matrix where each cell represents a similarity between a specific query token and a specific document token. In the next step, you will only select the maximum similarity for each of the query tokens and sum them up across all of them. The maximum score of our document for the query is around 17. Let's visualize this similarity matrix as a heat map. We have another helper function that does exactly this. Each cell shows how similar a specific query token is to a specific document token. Lighter colors indicate lower similarity, and the red border is used to highlight the highest score. You can see which query terms, like advantages or cars, match most strongly with which document terms, like benefits and fleets. This visualization helps you to understand why Colbert finds certain token pairs relevant. For clarity, all the mask tokens are removed from the query, but they also contribute to the final score. To appreciate the benefits of late interaction, let's compare Colbert with a traditional dense embedding model. You will load one of the popular embedding models from FastEmbed and use it alongside Colbert to see how the search results differ in practice. Now you will create a quadrant collection that can store both dense and multi-vector embeddings. You will keep the collection name and vector names as variables, so you can easily refer to them later on. Now the real collection setup. Notice the special configuration for Colbert. You enable multi-vector config with the maxim comparator, which tells Quadrant to use the maxim scoring that we discussed earlier. You also disable HNSW graph creation by setting the M parameter to 0, since this data structure cannot be effectively used for multi-vector search. Let's create some example documents about Quadrant and SQL databases to test the search functionality. Now you will insert these documents into the collection you created earlier. You will create both dense embedding and multi-vector representation using the Colbert model. Now let's search using both approaches. We'll create a helper function that will query the collection using Colbert embeddings. We pass the query and the vector is generated using the model you defined earlier. Please mind that you are calling query embed, not passage embed anymore, because certain models may process queries differently than the documents. You can also specify the number of results you want to retrieve. Another helper function will perform the same process, but using the regular dense embedding model. You have both methods defined, so let's create a query. Feel free to play with different queries to see different outputs. You might be wondering why we specifically selected this particular query. Proper names, such as the names of companies, are quite often divided into multiple tokens consisting of even single letters. Such a token cannot effectively represent what that particular company does, and it's more like a fallback. Even though we all know Quadrant is a vector search engine at this point, for our Colbert model, it's nothing more than a sequence of letters. To confirm that our query is divided into that many tokens, let's use the same helper function like we used before. Indeed, Quadrant was divided into 3 separate tokens, what proves that Colbert was not exposed to the name of the company in this training data. In dense embedding models, this kind of tokens will contribute to the final pooled vector, but they will be most likely just some kind of a noise. With token-level interactions, you can expect such multi-token sequences to be better matched between the documents and the queries. It's time to run search using both approaches to retrieve the results. Here you can see how long it took to generate Colbert dense vector and also how long it takes to return the results. We have another helper function with a simple visual comparing the search results of both methods. One key advantage of Colbert's token level matching is its ability to capture specific terms like proper names, in this case quadrant. Better than pooled dense vectors, since individual tokens retain their semantic identity throughout the matching process. Notice there are differences between Colbert and dense embedding results, but it's hard to say what was the winner. There is an overlap, but eyeballing is usually not enough. In real-world cases, we build reference ground truth datasets to ensure the returned results are of a high quality. What I'm noticing from this simple example is that all of the Colbert results mention quadrant, which is not true for the dense results, which is kind of expected because our query has mentioned quadrant. Let's check how each of the query tokens contributed to the score for the best result as retrieved by Colbert. We can use the same heat map like you used before. For that, we need the tokenization of both the document and query as well as their Colbert representations. A similarity matrix is the last missing piece. As all the components are ready, let's finally display the heat map. It's not surprising that perform and performance were the closest neighbors. However, Q, Tran, and T were also contributing to the final maxim scores quite significantly. So even though Colbert does not understand what quadrant means, this token level interactions helped to implement keyword matching. That was just a very quick introduction to how multi-vector techniques work for text. Let's join me in the next lesson to see what those techniques looks like for images.